Welcome to my final project presentation for Code in Place. My project is called Ancient Coding. Very simple, almost rudimentary program. What the program does is it allows you to input an equation of your choosing, whether it be a addition, subtraction, multiplication, or division problem at this point. And it will tell you what kind of problem it is, and depending on what system you'd like to choose to solve it, it will then show you how the ancient system that you choose would solve it, or it will show you from a modern computing perspective how the equation would be solved, which is very similar actually to the modern computing perspective, particularly to the Egyptian approach. So we really get to dive into the magic number there a little bit. My graphical interface was not working at the moment, and I have a new computer coming to me hopefully shortly, which will not break down in the process of using graphics, but at this point I think it will be cool to show you guys the program in the terminal and how it works. So I'm going to summon ancientcoding.py, and you can enter an arithmetic equation of your choosing. I'm going to try 8 times 9. I'm going to enter Russian peasant, the system of my ancestors apparently, and it has to be spelled right, and it gives me a bunch of information there. I print out the numbers, I collect them into lists, and to show you guys how the equation works here, this is an array of columns, and basically what it did here is it found that the larger number of the equation was 9, the smaller number was 8. In the Russian peasant system, it divides 9, or the larger number, by 2 while letting go of the remainder. The result is 1. It records the amount of times it did that, so I get index of about 3 times here, and then it superimposes that index over the second list where it multiplies times 2 number 8, 16, 16 is 32, 32 equals 64, so that the length of the second column equals the length of the first list. Now I'm going to take the indexes in the first column that are uneven numbers. 1 and 9 are uneven. Those relate to the index of 0 and 3. I use 0 and 3 as the index over my second column, which gives me 64 and 8. 8 plus 64, the sum of which is 72. That's how the Russian peasant system works. Let's try this a different way. So I'll try another multiplication program. Just to stay on the multiplication theme, let's try 5 times 17, and I'm going to type in Egyptian, and we'll see how the Egyptians did the problem. So what happens is that the Egyptians would use powers of 1 and 2 till the last power of 2 was just below the number that was a smaller number. So here I stop at 4 because 4 is just below 5. Then 1 plus 4 equals 5. I'm going to use the indexes here of 0 and 2. And if the second list, I make that list the same length as the first through multiplying the bigger number 17 times 2, which gives me 34. 34 times 2 gives me 68. Then I'm going to run the index, which relates to here, 1 and 5, because 1 plus 4 is 5. That gives me 0 and 2. And I run that over my second column, which gives me 17 and 68, which are at positions 0 and 2. Here is 17, 68, 0, and 2. And 17 plus 68 is 85. At this point for modern computing, I decided to simplify a little bit and give the user a chance to interact with the program. So I could enter something like 18 times 85. I'm going to choose modern computing, and it will tell you that computers make a list of zeros and ones using a very similar system with powers of 2 to what you might see the ancient Egyptians or even the Russian peasants doing, and then numbers that are being used in the equation to add up to sums of the numbers beneath could be seen as ones. Numbers that are not being used are seen or marked as zeros, and a chart that would be summoned that I'm not going to use to enter sum at this moment because my computer may crash, but that I've screenshotted from a website that's really inspired me, cutthemath.org, that I'm going to give a shout out to in a moment, would look a lot like this, where 216 equals 18. Therefore, I find the number directly across the next column, 170, 1360, 170 plus 1360 equals 1330, which is my answer. So these numbers would be marked as ones. The numbers in tan would be marked as zeros. And that would give you an idea of how a computer would do the problem, which is much more similar to how the ancients would do it than something like modern times tables, which can take years to remember and to memorize. And for me, kind of scared me away from math in grade school. Well, I found this to be really interesting and to kind of reinvigorating my interest in math in general. So with that said, thanks for checking out my program. Big shout out, extraordinary gratitude to all the professors and staff who brought this together. It's been a true honor and joy to be here. I'm sad it's ending, but looking forward to continuing with all the resources that have been offered, hopefully collaborating in the future in other ways. And also this program was inspired by Alexander Bogomolny, who's a wonderful mathematician, sadly passed away in 2018. Good friends with Nassim Taleb, who's another modern mathematician and thinker. Had some really interesting ideas in current interesting times that we're living in. But his website has lots of interesting algorithms and things you can go through, and some code even in Java to check out. Also, there's people that wrote code that I wrote much more simply and quickly, importing different modules like math, and using NumPy a lot more than I did. I tried to stick to for and while loops and what I learned in the course, and I really learned a whole lot doing that, sticking to simplicity and to basics, and that I didn't need to go outside of what I've known. So thanks to everyone who made this possible. I look forward to continuing, and it's been a true honor and joy to be here. Hope everyone's having a wonderful day or evening wherever you are, and I look forward to continuing to grow and staying connected in the future. Have a great night or a great morning, wherever you are. Bye-bye.